Welcome, operatives, to this tactical explainer. Today, we're treating your Chapter 14 syllabus on thermal physics like a high-stakes mission briefing. The objective is simple: extract maximum understanding so you can extract maximum marks from a hostile exam paper. We are going to completely break down the complexities of thermal physics into actionable, strategic intel. So lock in your focus right now, because we are about to decode the fundamental rules of thermal energy.
Here is your mission protocol for today. We're going to secure our base with thermal equilibrium, decode the tricky temperature scales, and then deploy two absolutely critical tactical tools: specific heat capacity and specific latent heat. Finally, we'll wrap up with a full debrief to make sure your extraction strategy is foolproof. All right, let's jump straight into Section 1, tracking net energy flow and establishing thermal equilibrium.
Now, you might just think of temperature as how hot or cold your morning coffee is. But here's your foundational intel. Temperature is actually a directional compass for energy. It tells us exactly where the energy is going to go. Thermal energy acts completely predictably. It will always move from an object at a higher temperature to an object at a lower temperature. And it's going to keep flowing until a perfect balance is struck.
Let's visually map out that exact flow so you can see what examiners are looking for. Look at the left side of this visual. If energy flows from object A to object B and then from B to C, logic dictates that A must be at a higher temperature than C. So energy is naturally going to flow from A to C. It's like water flowing downhill. But check out the right side. If there is no net energy flow between P and Q, and zero net flow between Q and R, then guess what? P, Q, and R are all sitting at the exact same temperature. When you hit that point of zero net energy flow, congratulations, you've achieved thermal equilibrium. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, so we know how energy flows, but how do we actually measure this out in the field? We can't just eyeball it. We have to observe how specific physical properties react as the temperature shifts. You could track the physical expansion of a liquid or a gas. You could monitor the change in pressure of a gas kept at a constant volume. You could even measure the shifting electrical resistance of a metal or the electromotive force, the EMF, produced across a thermocouple junction. These are your actual physical instruments for extracting precise temperature data.
Moving on to Section 2, we need to decode the temperature scales, specifically focusing on the thermodynamic Kelvin scale.
-273.15 degrees Celsius. Burn this number into your memory. This is absolute zero on the thermodynamic scale. This is the ultimate boundary line. It's the exact temperature at which all the energy that can possibly be removed from an object has been removed. At this specific point, substances reach their absolute minimum internal energy. Notice I said minimum, not necessarily zero energy overall, which is a key distinction. On the Kelvin scale, this absolute zero is literally 0 Kelvin. You can't get colder than that.
So how do we translate our everyday Celsius field data into this tactical Kelvin scale for our calculations? It's actually a very simple conversion rule. Temperature in Kelvin equals temperature in Celsius plus 273.15. Honestly, in a lot of fast-paced exam scenarios, just adding 273 is enough to get you the marks. Look at the data table here. The boiling point of water is 100 degrees Celsius, right? Add 273, and boom, it's 373 Kelvin. Or take something extreme like the boiling point of helium. It sits at a freezing -268.78 degrees Celsius. Add 273.15 to that, and you see it's a mere 4.37 Kelvin, just a tiny fraction above absolute zero.
All right, Section 3 introduces your first major calculation tool: specific heat capacity.
Stop scrolling! Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, back to the intel. You need to memorize this definition verbatim for the exam. Specific heat capacity, represented by the lowercase letter c, is the energy required to raise the temperature of a unit mass of a material by a unit temperature. The equation is C equals delta Q, which is the change in energy supplied, divided by the mass, times delta theta, which is the change in temperature. It's measured in joules per kilogram Kelvin. Let's run a live exam simulation using a classic worked example, the electric shower calculation. The mission here is to find the electrical current. First up, identify your equation. We know electrical power is voltage times current, but thermal power is mass per second, times specific heat capacity times the change in temperature. So we set them equal to each other. V times I equals m times c times the change in theta. Next, we input our variables. We have 230 volts. We don't know the current, so leave that as I. The mass flow rate is 0.12 kilograms per second. The specific heat capacity of water is a constant 4200, and the temperature heats up from 12 to 28 degrees, giving us a change of 16 degrees. Do the math on the thermal side, divide that by the 230 volts, and you isolate your variable perfectly to find a 35 amp current is required to heat that flowing water. It's a systematic extraction of the answer.
Moving right along to Section 4. Here is your second tactical tool, specific latent heat, which deals with state changes happening at a constant temperature.
Now, it is absolutely vital you distinguish between these two states to avoid losing easy marks. Latent heat of fusion is strictly for solid to liquid transitions. Think of ice melting into water. Latent heat of vaporization is strictly for liquid to vapor shifts. Think of boiling that water into steam. The critical detail for both: the transition happens without any change in temperature. All the energy is doing the hidden work of separating the molecules. The equation for both is L equals the change in energy supplied divided by the mass that actually changed state.
Let's run another simulation to lock this in. Imagine a 1.5 kilowatt kettle containing 400 grams of boiling water, left on for 5 whole minutes. The question asks for the mass of the water remaining. Step 1, get the formula down. Mass vaporized equals the total change in energy input divided by the latent heat of vaporization. Step 2, calculate your total energy. 1.5 kilowatts is 1500 watts. Multiply that by 5 minutes. But wait, we have to convert that to 300 seconds. That gives us our total joules of energy. Step 3, divide that massive energy number by the latent heat of vaporization for water, which is a given 2.26 million joules per kilogram. The calculation reveals that 0.199 kilograms, or 199 grams, of water has turned into steam. Now, step 4 is where students lose marks. Do not fall into the trap of stopping there. The mission asked for the mass remaining, so take your starting 400 grams, subtract the 199 grams that just boiled away into the air, and you've successfully extracted the final answer, 201 grams of water remaining.
And if they throw an experimental design question at you, which they love to do, just recall this specific apparatus setup. To measure the specific latent heat of fusion of ice in a lab, you use a funnel packed with melting ice, put a heater directly inside it, and sit the whole shebang above a beaker on a mass balance. You power the heater with a known wattage, let it run for a strictly timed period, and then measure the exact mass of the melted water that drips into the beaker. Because you know the energy you put in, and you just measured the mass of the ice that changed state, you can easily calculate the specific latent heat.
Operatives, we've reached the final debrief. Let's review the core targets we've secured today.
You can officially check these off your target list. You now confidently know that energy transfers from higher to lower temperatures until thermal equilibrium is achieved. You know that absolute zero is the absolute basement of the thermodynamic scale, and you can seamlessly convert between Celsius and Kelvin like a pro. Most crucially, you are fully equipped to deploy the specific heat capacity formula when temperatures are shifting, and the specific latent heat formula when a substance is changing state at a constant temperature.
Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. To keep your tactical skills razor sharp, I'm leaving you with this final high-level calculation to crack on your own. Every single day, a massive amount of solar energy hits Earth, and luckily, most of it is re-radiated back out into space. But what if there were just a tiny 0.1% decrease in the amount of energy re-radiated away? Think about the latent heat of fusion we just went over, and ask yourself, what extra mass of ice could be melted globally in a single year? It's a massive, real-world application of the exact formulas we just mastered. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep analyzing, keep calculating, and I'll see you in the next briefing.